Just to think a little bit more about the temperature model, let's consider a point halfway between these two sources. Now, other sources are far enough away that we can kind of pretend we've only got these two sources. This one would have some effect, but in any case, at this point, if we move directly toward one or the other of the sources, we kind of expect the temperature to rise. If we move perpendicular to one of those sources, we kind of expect the temperature to remain constant. So the gradient at this point, the direction of maximum rise, the gradient of a point maybe slightly closer to this one will be in this direction, slightly closer to this one, it'll be back in this direction. Let's say we go from this point now. The direction of constant temperature will be perpendicular to the gradient, so it'll be kind of like this. So this will be a contour line, and this will be a contour line. Now this contour line is going to tend to surround this source, and this contour line is going to tend to surround this source. Reason being that once we get out to this point, then, let's go just a little further to make it clear, we've gone a little too far, we're kind of off the contour, but now you see, being closer to this point, our gradient is not exactly toward the center of this, but it's more toward this than it is toward this. So now our curve is going to be in this direction, so that we're going to get a curve that kind of does this. Okay, now that's not very well drawn. It actually should have gone in a little closer here. But these gradients will be perpendicular to your contour lines, and of course we know gradients are perpendicular to contour lines. This will come in a little closer here, but now that we're getting into the influence of this temperature, to maintain a constant temperature we're going to have to start moving away from this one. So we're going to come out maybe here, and the contour line maybe go around here and come back in, and it'll close. Okay. We have some series of contour lines, and this contour line happens to cross the path. And the gradients more or less toward this source. Along this part of the path, we're getting pretty far away from the other sources. And I'm not trying to indicate the magnitudes of the gradients. These will have a little greater magnitude than these, I believe. What I'm trying to indicate, though, is at this point on the curve, if we're moving, let's say we're moving in this direction along the curve, then we have our direction of motion, and we have the direction of maximum temperature increase. If we were to project this gradient vector onto a unit tangent vector, we would get an idea of the rate at which the temperature is increasing with respect to distance along this curve. That would coincide with a directional derivative in the direction of the unit tangent vector, the directional derivative of this t of xy function. So let's say we have gradients of t of xy permeating the entire space here, permeating the entire area of our plate, and we have unit tangent vectors. At any point of the curve, we have a gradient and we have a unit tangent vector. So I'm going to kind of stick my neck out here and say that if this is a point of the curve, and this is our unit tangent vector, got a little notational glitch here. If I use t for my unit tangent vector, it looks a whole lot like the t that I'm using for my function. So I'm going to change my notation down here. I'm just going to kind of write over this and make kind of a fancy R with a little tail. Okay, and I'm going to call this R prime. R prime is also tangent to the curve. So we have the R prime tangent to the curve, and we have the gradient del t, and if t is a simple function, probably isn't for this situation, but if it was a simple function, that'd be a simple enough calculation. Then what we're saying is that the rate at which the temperature is changing as we move along the curve is the projection of the gradient onto the tangent vector. And it doesn't matter really whether this is a unit tangent vector or not. Easier to calculate the dot product and the projection if this is a unit tangent vector, but we don't want to mess up the notation, so I'm going to just say that right here is your projection. That's the projection onto R prime of the gradient function. And that should be the rate of change of temperature with respect to position on the curve. I'm not going to present an entire argument to justify this, but let's just say intuitively this makes a certain amount of sense. Now, just make a pretty straightforward statement. Let's do it up here. The temperature reaches a relative maximum or minimum when the rate of change of t of xy with respect to position on the curve is what? If you reach a relative maximum or minimum of the temperature, that means the temperature is all the way up and it's not going up or down anymore. That means that the rate of change is 0. And similarly for minimum temperature, if the temperature is down as far as it'll go, it's not going down anymore. For the instant it's not going up anymore, its rate of change is 0. Now that's the rate of change with respect to position on the curve, not a rate of change in 2 dimensions, but with respect to motion along the curve. If my assertion is correct and the rate of change of the temperature with respect to position on the curve is the projection of delta t onto your tangent vector, then we conclude that we have a relative max or min, that if we have a relative max or min, that implies then that the gradient of t at that point is perpendicular to r prime. Because of course the projection of one vector onto another is 0 when those vectors are perpendicular. An equivalent condition is when delta t dot r prime equals 0. And that's del t, lift the t out, dot r prime equals 0. And equivalent to this condition is that delta t is parallel to the unit normal, any normal. And being any vector perpendicular to the curve. Next clip, we're going to generalize this idea to a surface in space. So we want to, say, maximize the temperature function in 3 dimensions relative to a sphere or an ellipsoid. Where on the ellipsoid, where on the sphere is the temperature going to reach its maximum? And when we get into more than 2 dimensions, normal vectors are going to be more useful than tangent vectors, because when you get into 3 dimensions, a tangent vector to a surface, you can have infinitely many tangent vectors to a given surface. You don't have just one direction for a tangent vector, but you do have tangent planes and tangent hyperplanes, which have normal vectors that, as we've seen, we can easily enough calculate, provided we have reasonably nicely defined surface.